today's lesson, we are going to be looking at doing titration number 3, which is our redox titration calculations. Now, in this question, they've broken it down into A, B, C and D. Sometimes you'll be given the 2 half-ion electron equations and expected to write an overall redox, which is a higher skill. That would be worth 1 mark in an exam. However, this one has given us an overall redox, and the final question wants us to calculate the mass percentage of iron in the steel. So we want to identify our reacting particles. So what I'm working with is I'm working with my iron, and I can see that it is also giving me information about permanganate, which is my MnO4 minus ion. So what we want to do is we want to take these down, Fe2 plus, put it in a box, reacting with MnO4 minus. But what I can see is from the balanced equation that 5 iron 2 pluses react with 1 permanganate ion. So we want to take our ratio down as a 5:1 ratio. The question wants us to calculate for part A of the number of moles of permanganate. So on this side, we would do N is equal to C times V. If we read the numbers backwards, the concentration of the potassium permanganate solution was 0.05. multiplied by the average titer, which was 16.4, divided by 1,000 to put it into litres. So we do 16.4 divided by 1,000 times by 0.05, and that tells me that 8.2 times 10 to the minus 4 moles of permanganate had reacted. We put it underneath here to use that as our scalar, 8.2 times 10 to the minus 4. 8.2 times 10 to the minus 4, and to cross multiply we want to times by 5 and then divide by 1, and that means that the number of moles of iron which had reacted was 4.1 times 10 to the minus 3. So that's the number of moles in 25 centimetres cubed. So 4.1 times 10 to the minus 3 were found in the 25 centimetre cubed samples of the iron solution. However, that was only an aliquot, a small sample of that. We have to scale it for the standard flask. So this is the sample, and we need to scale it for the standard flask, which was 250 centimetres cubed. So to scale that, we cross multiply, so we would times that by 250, answer divided by 25, and that means that the number of moles of the iron 2, which was found in the standard flask, is 0.041 moles. We then want to calculate the mass of iron. So mass is equal to number of moles times GFM. The number of moles we'd calculated for the standard flask was 0.041 times by the GFM of iron, and that is 55.8, times by 55.8, and that gives me a mass of 2.2878 grams. And we want to express this as a percentage mass. So remember, percentage is equal to mass over sample times by 100. The mass we carry through, 2.2878, over the sample size, which was 2.49, times by 100. So divide that by 2.49, answer times by 100. And that gives me 91 point, and I want to look at the significant figures. They've given me 3, so I'm going to make this 7 my rounder. So that's going to be 91.9%. This past paper questions from the Advanced Higher 2022, written 7B part 2. The question wants us to calculate the mass in grams of the iron 2 ions in the lawn sand sample. So what I can see here is I know that this is redox, and the reason I can see that is because I can see both types of ions on the left hand side of the equation. I've got my iron 2 ions, and I have to look at what it's reacting with. In this case, it's the dichromate solution. So I take these entities down, and then I need a mole ratio. I've got 6 reacting with 1 of my dichromate. If I'm using the numbers backwards, I can see I'm given information about the potassium dichromate solution, and therefore I want to calculate the number of moles because this is my mole ratio. N is equal to C times V. The concentration is 0.005 times by the average titer, which was 21.4, divided by 1,000, and I put that into my calculator. 21.4 divided by 1,000 times by 0.005, and that gives me the actual number of moles of reactant dichromate as 1.07 times 10 to the minus 4. I want to then put that in as my scalar, 1.07 times 10 to the minus 4, and then we're going to cross multiply. So to do that, I need to times by 6, answer divided by 1, and that will allow me to scale for the number of reactant iron 2 ions, which is 6.42 times 10 to the minus 4. Now what we can see there is the number of moles which had reacted in 25 centimetre cube samples. So we've got 6.42 times 10 to the minus 4, which had reacted with which were found in 25 centimetres cubed, which was my sample size. However, that sample was taken from my standard flask, so I have to scale for that. And my standard flask was 250 centimetres cubed. So I would need to cross multiply to scale for the actual number of moles that we've got all together. So to do that, I would times by 250, answer divided by 25. So my actual number of moles is 6.42 times 10 to the minus 3. We then have to, so that's 1 mark. We then have to calculate the mass of iron. Mass is equal to N times GFM. The number of moles was 6.42 times 10 to the minus 3 times the mass of iron, which is 55.8, times by 55.8, and that would give me a mass of 0.358236 grams. It wants me to work out that's it. Thought it was going to ask me for the percentage mass. What we have to do, however, is we have to round to the correct significant figures. I can see that they've got 3 sig fig, so I'm going to use this as my rounder and round this at 0.36 grams as my final answer. This past paper question is from the Advanced Higher 2017 Written 10. The question wants me to calculate the concentration in moles per litre of the hydrogen peroxide and the undiluted stain remover. So what I can see is my 2 reactant particles. I've got my potassium permanganate and my hydrogen peroxide. So I want to take that from my balanced equation and do my ratio, which is a 2:5 ratio. If I'm using the numbers backwards, what I can see is I've been given a table of the permanganate solution. So this time I'm going to be working on the left hand side, and what we have to do is we have to actually work out the average titer. So we need to look for concordant results, and that means that the volume used has to be within 0.1 centimetres cubed. So we're going to be using titration 2 and titration 3. So titration 2 has 8.5, titration 3 has 18.6, and that's because there is 0.1 centimetre cube difference. Divide that by 2 to take an average, which means my average titer is 18.55. So on the left-hand side this time, we're going to calculate the number of moles. Number of moles is equal to C times V. The concentration of the permanganate solution was 0.03 times by my average titer, which was 18.55, divided by 1,000 to put it into litres. Divided by 1,000, answer times 0.03, and that gives me the number of moles of reacting permanganate as 5.565 times 10 to the minus 4. I want to use that as my scalar, so I put that here, 5.565 times 10 to the minus 4, and I'm going to cross multiply to scale across. So to be able to do that, I would times by 5, answer divided by 2, and that gives me the number of reacting hydrogen peroxide as 1.39125 times 10 to the minus 3. Now, This number of moles was found in a small sample. The 1.39125 times 10 to the minus 3 was found in a 20 centimetre cubed sample. However, we have to make sure that we scale it for the standard flask, and we see that the standard flask is 100 centimetres cubed. So to scale that, we would want to times by 100, answer divided by 20. And that would tell me that the number of actual moles that we've got altogether of our hydrogen peroxide would have been 6.95625 times 10 to the minus 3. The question doesn't ask us for that, it asks us for the concentration. So concentration is equal to number of moles over volume. The number of moles we carry through is 6.95625 times 10 to the minus 3 over the volume that they've given us of the initial stain remover, which is 5 centimetres cubed. So we would do 5 divided by 1,000. So if we divide that by 0.005, that will give me a concentration of 1.39125. I need to make sure that I'm rounding that to the number of significant figures. So I want to do 3 sig fig. So I'm going to round that to 1.39 mole per litre.